Thank you, everyone. So I'm a machine learning engineer, and my idea of quality, as I found out this time, being the first time here, is completely different from the idea that most of the QA testers and QA program managers have. In fact, I'm probably one of their worst nightmares. And that is why we have Mona on the call. She's been in those roles. She's been a developer and she's been a tester. So I'm going to talk about the problem of quality with machine learning models and what we understand as data scientists, machine learning engineer to be quality. She's going to talk about the solution, having been on your side of the fence. And with that in mind, let's get started. I'll just press here and go to the next one. So you see my picture a few years ago. I had less white hair. And you see Mona that you cannot see, but Mona, if you want to say hello and say a few words about your role.
Sure. Thank you, Giovanni. Hi, everyone. I'm happy to join virtually. I'm also a machine learning customer engineer, and I've been in this industry in machine learning for 6 years. And before that, I was a Java developer. And that's why I will talk about some of the ways how software quality relates to machine learning quality. I will talk about those things. I'm really happy to join virtually and talk about this. Thank you.
Okay, so let's go and have a look in the world of machine learning engineers. What do we worry about? We worry about models, and we worry about defining what a model should be doing. How do we differentiate between a good and bad one, and which measurements we take of those models to make that differentiation. Then we use those measurements to test their quality. We have a process, of course, to automate this testing, but not only the testing, the training and evaluation of those models as well. And I'll explain why that is also important. And last but not least, as Google, we have a set of tools for all of the above. So let's start by framing the problem. And I apologize for the math, but that's the world I live in most days. There's a lot of math in the process. So what does a model do? In its simplest implementation, a model maps a set of inputs, set of outputs. It's a function that takes X and creates Y. In machine learning, the learning word is the key. The model is learned from the data. It's not given. And when you think about most of the mathematical models of modern science, even the most famous one, E equals mc squared, that is derived from deductive reasoning. It was years before Einstein could actually, well, it was dead when it was proven true looking at the data. In machine learning, we do it the other way around. We look at the data and we come up with F. So how do you test a model? Well, the same way that you test a program. You give it a test set of X and Y, where you have a known input and a known output. But the key in this process in machine learning is that you have a desired output. You're not sure that you're going to get it. Models are statistical in nature. So there is a random element in there that you need to account for in your testing process. Now, we start developing models by training and evaluating them for fitness, for purpose. The reason why I am stressing this is that in the machine learning world, a model is the sum of its parts. It's a sum of its data, its code, its training process, and the evaluation set that is being tested again when it was produced. All of them make it up. So they are effectively parts of a system. And the way that you differentiate between a good and a bad model is by understanding whether it will support the system goals or not. A good model should be supporting system goals better than a bad one and make fewer mistakes than a bad one. Now, that's a conversation I had over lunch In QA, you expect to iron out all the mistakes. In machine learning, you expect to have mistakes. And you actually want them because otherwise the model may be overfitting its data set. So it's a completely different optics that you start this quality discussion from. And I want to quote a famous statistician that came out with a book in 1987, as far as I remember, George Box. His main contribution was finding a way to make non-normal distributions normal. But he said famously that essentially all models are wrong, but some are useful. And if there's anything that you take away from this presentation, remember this phrase. We start in machine learning knowing that all models that we come up with are wrong. How do we make them useful? That's really the focus of quality control, if you want, on a machine learning model. Now, I want to introduce two cases as examples for the process that we go through to justify the quality or evaluate the quality of a machine learning model. Let's take, for instance, two common problems. One is classification. And there, in classification, for instance, we're trying to establish whether something is true or false, or whether we retrieve interesting, relevant data or irrelevant data. Being Google, that's a problem that is quite to the core of our business. We have to give you relevant results. So there are a bunch of measurements that will judge the quality of a classification model. And I have listed them here. The most common one is accuracy. How many times do I get it right over the total number of cases? Others that you may have come across are precision and recall. Precision is if I tell you that something's going to happen 10 times, how many times out of those I tell you, I'm actually getting it right. And recall, out of all the possible cases that are positive, how many times do I get it right? How many of them do I get out? Which measures you use, and therefore how useful your model becomes, depends on the system that it is part of. An example that is often quoted by Google employees like us is the work that we've done on breast cancer screening. There are models that are used in radiology to help the radiologist figure out whether that particular picture contains cancer cells or not. Which measure do you think that is most useful in this particular case? Any takers? Accuracy? Well, it's actually recall, because we want to make sure that we save the patient's life. If it was precision, we would save the doctor's time. We tell them that this case is actually cancer, and they go look at it, and it is, and do whatever they need to do. But there may be things that are missed. So if I was to develop a model that as any medical application, recall would be the measure that I tune for, the measure by which I judge the quality and the usefulness of my model. Now, in regression, which is another more common, very common use case, it is not as intuitive to figure out which measure to use. I'm listing here a few of those that you may come across, such as the mean average percentage of error, or the mean average error, or the root mean square error, or the determination coefficient. The last two are actually the ones that are used most often. The example I have found is very applicable to today's economic environment. It's a law called Occam's law that was designed in 1962 when things were going all right, I'm told. I wasn't around at that time, although I am old, I'm not that old. Basically, this tells you that for every change you want to affect in terms of percentage in the unemployment rate, there is a 4% point change that has to happen in GDP. And that is often the case when things are more or less predictable. But in 2008, with the major Lehman Brothers induced crisis, things were all over the place. Look at the path that those data points took. So Occam's model validity was badly tested. And in today's environment, with the inflationary environment that we are in, the graph is similar. I couldn't actually find the most recent data, so I'm stuck with a 2008 graph here. So if I wanted to create a model today that improves on Occam's law, which measure would I would pick the root mean square error because it penalizes the outliers. It has a square element. So that's a way that I would make that model more useful. Or I would create a new one using that measure for today's working environment. Another way to judge the quality of this regression model would be the determination coefficient, the last one, which basically tells you how much of the variance in your data set can your model capture. You can have a pretty good root mean square error and yet be looking at things completely wrong. And your determination coefficient is very low. It's typically between 0 and 1, and you're close to 0. In an ideal world, you want both of them. Well, you want the determination to be close to 1 and the root mean square error close to 0. So those are the two that you typically look at to judge not only whether your model fits the data, but whether you're looking at the right thing when you create the model. With those measurements in mind, you start training the model. And then you find that your training process may be generating a model that's underfitting, overfitting, or just right. Underfitting means that the model cannot actually learn from the training set. That's the picture on the left. And if you were to look at the measures, such as the R squared, the determination coefficient, it would be pretty low in that case. It means you're looking at the wrong thing, that your model is not actually doing what it's supposed to do. Overfitting, too many degrees of liberty, if you want, it's on the right. You're trying to fit all the points. And that's the illumination that came from lunch. That's what QA tends to do, trying to cover all the cases. We don't want to cover all the cases. We want to have a model that's just right, like the one in the middle. And if you're wondering where this comes from, it actually comes from a case that we worked on transport utilization during the pandemic. Turns out that when we started recovering from the pandemic, the utilization went up more or less like a fourth order polynomial function. So these models are not, plucked out of nowhere. They have a practical application, and increasing the degree of that function, the complexity of that model didn't get us any better results. We were looking for a thing in the middle so that transport authorities could actually invest in the right routes at the right time and in the right place. So with this brief introduction into things that you need to worry about, so which measure, for what purpose, and whether your model is actually fitting the data correctly or not. What do you do? How do you monitor that the model code that you've been given is actually fit for purpose? So you start with a training process. You monitor the training runs for overfitting, underfitting, and convergence. And you're seeing here the output of a tool called TensorBoard that Google produces, which is used to monitor the progress of training of these particular models, both on premises and in the cloud. We have both implementations. And in this particular case, we're looking at training loss and training accuracy. So, and similarly on the valuation set. That's another thing to keep in mind. While in normal QA, you try and cover all the cases, in machine learning, we on purpose leave out some of the cases for valuation and testing so that we can test the ability of the model to generalize. Typically, you have a training process that includes evaluation step and a out-of-band test step of the trained model afterwards. This particular graph here is showing you the training of two variations of the same model. Actually, one is blue, the other is red. And it's highlighting that although the training actually progresses relatively smoothly, there are some oscillation in the valuation of that particular algorithm on the valuation data set. You're seeing here that the red line, for instance, reaches the minimum loss and the maximum accuracy at about iteration number 7. And then it actually gets worse before it gets better again. So what this is telling me is that by using this training tool, this monitoring tool, I can actually stop my training at iteration number 7 and save myself some computational cost and effort. Ultimately, I actually get the better results by stopping earlier rather than trying to input even more cases for the algorithm to cover more. As we provide test cases, training data sets, test cases, parameters, etc., to the training process, we will want to compare experiments. Same algorithm, different set of parameters, or hyperparameters as they're often called in jargon. Different number of iterations, for instance, that's one of the hyperparameters that we've seen before. The advantage of being able to run in the cloud is that you can run several of these experiments in parallel. And then we collect and collate the results and look at one of those measures by which we judge the quality of the model, accuracy in this particular exercise. And you'll see that pretty much out of these 5 models, they're all pretty decent except one. The second from the bottom has a lower accuracy rate, by not that much, but lower. So in this particular exercise, I would go with one of the models that is simpler, such as this one. Maximum depth of the neural network is 3. So it's simpler, takes less to train, and it still gives me a pretty high accuracy. That's the one that I would pick in that case. But I need to run these experiments because we don't know a priori what the result is going to be. Let's now, having talked about the training and evaluation very quickly, let's now look at testing and the problems that exist in testing the trained model. The first problem is just understanding what testing this model is about. Programs typically have known specifications. You're given a test case and you get an expected result. And you want to get that consistently. You give the same test case, you get the same expected results. In most cases, that's what happens in software engineering. We know that the test set is consistent, but it may be incomplete. I mean, unless we're geniuses, we cannot cover all the bugs for everything. So we accept the fact that it's incomplete and consistent. Models, on the other hand, have no formal specification. There's data, their code, the hyperparameter that we use for the training. See the different versions of that model give different results depending on the hyperparameters, and the training process itself, 7 iterations, 10 iterations. We have to test all of those cases, and we always expect a certain percentage of the results will be wrong because we on purpose left out a portion of the data set so that the model can generalize on things that it's not seen. There are other aspects to consider. In most cases, practical aspects, the inputs that you get to train your model can be noisy, can be mislabeled. Humans make mistakes too. I need a radiologist to give me images of X-rays to train a model, and radiologists make mistakes. So the input itself may be inconsistent. The inputs may also not cause all possible outcomes. Our test set is incomplete. Models themselves are non-linear. Neural networks are designed to be non-linear so that they can actually represent non-linear phenomena. And they can also be chaotic. So a small variation in input can cause a huge variation in output. I'll give you an anecdotal example of that. You probably realize that I have an Italian accent by now. When Siri, I work for Google, so I can say Siri, came out in its first iterations, when I tried to talk to it, it would always assume that I was looking for a restaurant. Whatever I said, so small variation in input, huge variation in output. It was giving an answer, but it was one of the edge cases. They hadn't actually trained the models to deal with English speakers, English as a second language speakers. So even famous actors made videos on YouTube where they were speaking to it in a Scottish accent, for instance, and it would give them completely irrelevant results. So that's actually an example of how the system can be chaotic, these neural networks. So how do we cover for that test case? First of all, we want to select a subset of the data that is representative for all the important cases and all the important population groups. Having established that our data set can be inconsistent and incomplete, the closest thing that we can get to a regression testing is a subset where we absolutely must have consistency. And for that subset, we want it to be complete. We want to cover all the cases. An example with Google Photos, for instance. Google Photos will let you tag faces and say, this is me, this is my wife, these are my kids, etc. We want those family members to be consistently recognized across the photos and across the years. Kids grow up. Secondly, we want to have independent train, test, and validation data for the generalization problem to be solved, and also to prevent leakage. If you have time series data, you need to predict the future based on the past. You don't want to leak data from the future into the training set. Thirdly, and this is the most difficult one, algorithm coverage. There are a gazillions of different algorithms. One of the simplest ones is decision trees. Decision trees are relatively simple to understand, and that's why they're also simple to explain the results back with. They're very popular in public sector for that exact reason. You want to be able to justify every decision that is taken by a decision tree, so you want to be able to cover all the paths in a decision tree. Covering all the neurons in a neural network is another story. Neural network models, as I said, are highly nonlinear, highly complex, possibly chaotic. And therefore, you don't even know what the expected output is in some of the extreme cases. There is actually a very interesting paper that I've linked in that explains how that is the case and why it's a desirable thing. Do you want to model highly nonlinear and chaotic systems? Because that's what reality is. So that's where you want to go and curate your data sets and then evaluate the test results. There are other things that must be taken into consideration for practical applications of this trained model. I mentioned the regression case, perform well consistently on the important inputs. You also want the model to be fair. They have comparable performance across important subpopulations of your data sets. So going back to that example with Google Photos, you want the model to be age blind. My kids grow up, so I want them to be recognized as my kids as they age, so as their face changes. So the model is age blind. Is that realistic? If you've used Google Photos, you'll see that it's realistic within certain age bands. It doesn't cover everything. And that's the third point, reality check. It is acceptable in this world to have lower performance on outliers. Dark, fuzzy pictures, picture of a kid at 2 months old, picture of a kid at 18. It's not going to recognize it. The key is in identifying those outliers, and therefore that the prediction that the model gives you is not reliable. So you give a confidence score with the result that the model produces. And as you train these models, you have to have a way to compare the results across those sets for consistency across the important cases. This is a screenshot from a dashboard in our Vertex AI product that lets you compare different models. Now, as you can see, there are several measures calculated, including precision and recall. If I tell you that the model that you're looking at is X-rays for pneumonia, which measure do you think now that we've discussed it is the important one? Any taker? It's still recall. It's still a medical case. Now, there is, however, a further consideration to be made. You want to be able to figure out where the mistakes lie and why they are there, because not all the mistakes are random. As I mentioned, models are affected by bias in their training input, and therefore you want to evaluate equally for subpopulation groups. Not all the mistakes have the same impact once you've made them. So in the example that I've just given you, the one of X-rays, a subpopulation is significantly underrepresented, and that's kids. The data set is public, by the way. You can try this on your own if you want. And we publish actually the guidelines to do so. So in order to take those into account and be aware of what's going on, you want to monitor for bias in the inputs, and you want to monitor for skew and drift in the output. Skew is the difference between your original training data set and the distribution of the data that you're being presented in production. Drift is the change of forecasts over time. Both indicate that the model may no longer be fit for purpose and raise an alert. If it's given data it's not trained upon, it's highly likely that there will be a higher error rate. If it drifts over time, it means that the data in input is also changing, and there will be a point where it's no longer fit for purpose. The other thing that we don't always mention is that you need to monitor for the amplitude of those errors and the frequency. That's an additional signal that things are about to go wrong and you want to do something about it. And last but not least, models are not fair. If there's bias in input, you don't get a fair model in output. So you want to be able to explain the results back and check why certain things are judged to be in that way or not. So that, again, the people that are the subjects of that model understand that why, and you as a developer of that model can fix it if it's wrong. Example that I've given you with the X-rays before, the false negatives. I've actually talked to a friend of mine who's a doctor and tried to figure out why these were false negatives. They are X-rays of kids. There aren't enough images that's in the input data set for the model to correctly predict pneumonia in kids. So there's a bias in input, which has a disproportionate impact in output. Kids are the most likely to die from pneumonia. Their immune system is not completely developed yet. So by making this mistake of using a biased data set and releasing this model, we are putting kids at risk. Now, of course, this is a public data set. It's a known problem, and no clinician is using this model. I've just trained for demo purposes, okay? No kid was armed in the making of this demo. So I've talked about the problem now, the need to establish a good measurement set fit for purpose, monitor the training for convergence and for generalization ability, establishing good coverage within the limits of incompleteness and inconsistencies that the problem has for a test case. Now, how do we in practice do that? I want to mention a couple of things and then I'll hand over to Mona. It's a process that we suggest in 4 steps. Curate the data set with multiple training, validation, and test sets for subpopulations and covering the critical regressions. And therefore, establish version control, not only for the code, but also for all these data sets that you're feeding in. Automate the process with pipelines for repeatability. And the pipelines, when they run, have a set of parameters that you pass to the training algorithm. So also those need storing. Cross-validate for robustness. So take different sections of the data and swap them out as training test sets. Evaluate and compare. Evaluate different models, compare the results, pick the most efficient or the one that's best fit for purpose, and explain the answer by attributing the feature importance. That's actually one thing that I missed. Feature importance is that green mask. It's telling you which pixels actually led the model to make that determination that this case was pneumonia. Then continue to evaluate, not only in testing, but in production, monitor for drift and skew. Being Google, we have a library for everything. We have a library for this process. It's called TFX, or TensorFlow Extended. You see the main components here. I'm not going to describe them in detail, but they cover the process that I mentioned before. Of course, this works for TensorFlow, and there are other frameworks around. So our tools extend to those other frameworks. It's just that this library is the one that we come up with and that we use internally. And it's available to you as open source as well. And I mentioned pipelines as a way to automate the process. We have a tool called, unexpectedly, I would say, Vertex AI Pipelines that does exactly that. And you can see a graphical representation of one there. They run parameterized processes on a serverless infrastructure. And with that in mind, I'm going to hand over to the expert on this. Mona, can you take over from now?
Sure, thanks, Giovanni.
Okay, go ahead. I'll switch off the mic.
So do you want me to share my screen? I don't think I have a way to share my screen. Oh, let me check sharing my screen.
I can just click next on the slides. That's fine. Just tell me what you want me to do.
Can you see my screen?
No. I'll stop sharing, but can you share yours? Yes, there you go.
Okay, perfect. Thank you so much. Hi, everyone. So Giovanni, what Giovanni has, can you hear me?
Yes, I was just told that we have 5 minutes.
Oh, we just have 5 minutes. Okay. I wanted to cover, I'll skip all of this. I wanted to quickly talk how Vertex AI can help with model quality. And before that, what is Vertex AI? Vertex AI is Google Cloud's unified development and deployment platform for data science and machine learning. And it offers the challenge with all of this, and the challenge with machine learning process itself is that to do end-to-end testing of your model from writing multiple experiments to picking the right model with the best score, best performance accuracy score, and then deploying that model in production, and then building that production pipeline and thinking about setting up A by B testing, and then also thinking about stress testing. All of this is infrastructure heavy lifting. And what Vertex AI pipeline does, it makes it easy for you to manage your machine learning workloads serverlessly with some of our offerings. And also it gives you solutions where you don't have to worry about infrastructure management. You are focusing just on the quality of model by tools such as Vertex AI, explainable AI. So with explainable AI, you can just with one click have explainability in your model. We have something called model monitoring. Since we don't have time, I'm not going to go into the demo, but I will share the links where you can go and watch these demos. What model monitoring does, Giovanni discussed about training serving skew in the model, which is a big problem to monitor. You have to set up complicated tools to do this today as a QA engineer. So what model monitoring does is automatically detects for if schema changes of your model or your prediction label changes. So you can set up those monitoring alerts, and it automatically monitors for these alerts in your deployed model in production, and it will alert you. So you know before that what is happening. Talking about model registry, it is a place where you can come for traceability, versioning, auditability of your model. And also we have machine learning metadata service where you can come and check all the metadata and all the lineage of your model. So, and we also have Vertex AI pipelines. Giovanni showed you that TFX TensorFlow extended steps, that how easy it is to create those pipelines. But the actual challenge with TensorFlow extended, creating those pipelines, and also with Kubeflow pipelines is that you will have to run a container and orchestrate all of these steps, right? And there can be multiple orchestration happening. And that is why we have Vertex AI pipelines, which does out of the box serverlessly for you. So you can set up either Kubeflow workloads or TensorFlow workloads, and you can define this is my model, this is my data creation step, this is my feature engineering step, this is my training step, and this is my deployment step. And also as a QA engineer or as a quality control system, you can have a quality control that only deploy my model if the threshold is more than this quality I want. So you can set those deployment threshold. This is all ML ops, similar to how you will do quality testing, CI/CD in your software quality system. This is how you will do in a machine learning systems. Since we do not have a lot of time, I also want to talk about model cards and what are model cards. Model cards is something you can think of that when you go and buy a product, you look at the nutrition facts, right? So what model cards does is that it's come from Google research, and it's a way to know the limitations of a model. And once if you know the limitations of a model, it's very, very easy to work with a model and explain as a developer. And it is very easy to explain why my model predicted something. Is there a bias? Is there a fairness there? With this, I will take a pause and jump to last. Skip all the demos. And we'll share the link so that you can watch it later. Thank you so much. I'll hand it over to Giovanni for any questions. And you can connect with us on LinkedIn if we are not able to answer the questions now.
I'd like to say that we have one question on the Q&A panel. If time permits, maybe question as you move forward here. So Giovanni, can you take the question on the Q&A screen?
Yeah, I'll read it back to the audience here. It says that for data sets that you use for training testing, are they real data or fake data? And if you use real data, how do you take care of security or how to protect that data? So in real use cases, you want to use real data. There are a set of benchmark data sets that you can find on Kaggle or other open source that are used just for that benchmarking. But since a model is the product of its data, its code, and its training, you want to train on the real data set to solve a production problem. As how you solve the security aspect of the data sets, there are a variety of techniques that we use in Google Cloud for every data. So there's, of course, mechanisms for authentication and authorization, encryption of those data sets. There's a tool which we called a data loss prevention that actually strips private information from the data. In the cases that I've shown you, for instance, there's really no reason to have the name of the patient. You only train on the image. So you strip away the sensitive information from those data sets to do the training. And also, you leave the data in the customer's account. So I'll use public data sets here. If you train on Google Cloud, contrary to public perception sometimes, we don't actually see the data that you train on. We don't read your data sets. We don't view your images. You own that data and you control and govern it with whatever standard protocol that you want to apply.
Thank you. Very
Yeah. Okay, we were talking about it at lunch with my colleagues here in the room, Brianna and Derek. There are mainly two big areas of applications. One, as you can probably expect, is document processing. Google has a solution called Document AI that will let you perform a variety of tasks on documents, both files and scanned images, like extraction of text, key value pairs extraction, layout extraction, and etc. And then you put those data into a data warehouse, and then you can search, query, and do further processing with those. The other area of application is actually video processing. Think of all the video streams that are generated by traffic cameras, for instance. We do things like counting the number of cars, so traffic flows, counting the number of people for people management at intersections and all that. Blurring the faces, again, to protect the privacy, or blurring the number plates of cars that go through a toll system. All of those types of applications in video and documents are quite common in the public sector. Others are specialized models for specialized use cases. So public sector is either very generic or very specific. They don't seem to have a lot in the middle.